Welcome to Orbit Observer. It's lovely to have you here tonight, wherever you happen to be. Maybe you're lying in bed with the lights already off, just the soft glow of a screen and the weight of a blanket pulled up to your chin. Maybe you're on a couch with one lamp still on across the room, the kind of light that's more for company than for seeing. Maybe you're somewhere stranger than that, a train carriage rocking gently through the dark, a long drive winding down, a quiet room in a part of the world where it's already deep into the small hours. Wherever you are, I'm glad you found your way here. And I'm curious, where in the world are you watching from tonight? What time is it in your corner of things? Leave it down below if you feel like it, before you drift off. I always love reading where these quiet little journeys reach, and if you enjoy these slow wanders through space and the strange physics of other worlds, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. So if you'd like more nights like this one, more soft hours spent thinking about planets you'll never visit and would probably not survive, that little tap means a great deal. And to those of you already here, already subscribed, already part of this quiet ritual, thank you, truly. You're the reason there's a next one. Now, let me make my usual promise to you, the one I make at the start of every night. We're going to take this slowly. There is no rush here, none at all. I'm not going to quiz you at the end. You don't have to follow every thread, or remember every number, or hold the whole shape of it in your head. If you drift off somewhere in the middle of a sentence, that's not a failure. That's exactly what this is for. The ideas will still be here. They've been here for billions of years, in one form or another. They can wait for you. And honestly, if this turns out to be so interesting that it keeps you awake, well, at least you'll have learned something. A fair trade, I think. So settle in, get comfortable, let your shoulders come down from wherever they've been hiding all day, and let me tell you about a place where you could step outside onto an alien surface under an orange sky without a pressure suit. I want you to really sit with that for a moment because it's stranger than it sounds. Almost everything we imagine about living on another world comes wrapped in the same image, doesn't it? The bulky white suit, the glass dome of the helmet, the hiss of recycled air, the constant low-grade terror that a tear in the fabric or a cracked seal could end you in seconds. That image is so fixed in our minds that we barely question it. Of course you need a suit out there. Space is a vacuum. Other worlds are hostile. You armor up or you die. That's just how it works. Except on Titan, it isn't. Titan is the largest moon of Saturn, a world wrapped in a thick, hazy, golden atmosphere so dense you can't even see its surface from space with ordinary eyes. And down on that surface, the air presses on you at about 1.5 bar. Let me put that into something you can feel. 1 bar is roughly the pressure you're sitting in right now, here on Earth at sea level. The weight of the whole sky resting gently on your skin, which you never notice because you've felt it your entire life. Titan's surface pressure is about 1.5 times that. A little heavier, a little thicker, not crushing, not dangerous. If anything, it's a pressure your body could simply live in, which means, and this is the part that quietly rearranges how you think about the whole subject, you would not need a pressure suit on Titan, not the bulky, armored kind. You'd need to be warm, desperately warm, and we'll get to the brutal reason why. And you'd need oxygen to breathe because there's none in that thick air to fill your lungs. But you wouldn't need the suit. You could walk Titan's surface in something more like a heavy insulated parka and a mask over your face. Picture a cold weather scuba diver. That's closer to the truth of it than an astronaut. Bundled up against the cold, breathing from a tank, but otherwise just a person, standing on the ground, under a sky, in air that holds you the way Earth's air holds you. No countdown, no catastrophic decompression waiting for one weak seam. We know this all, and I want to be careful to always tell you how we know things because that's where the trust lives. We know this because we sent something there. In 2005, a small probe called Huygens, built by the European Space Agency, fell through Titan's thick orange haze on a parachute and landed on its surface. It measured the pressure. It measured the temperature. It tasted the air, in a sense, with its instruments on the way down. Huygens rode there aboard a larger spacecraft called Cassini, a joint mission flown by NASA, the European Space Agency, and the Italian Space Agency, which spent years orbiting Saturn and mapping its moons. So this isn't a guess, this isn't a thought experiment dressed up as fact. A human-made machine sat on Titan's surface and told us directly what the pressure there is, 1.5 bar, survivable, almost comfortable. And yet, here's the strange thing, the thing I'd like us to gently pull apart over these next few hours. Almost nobody talks about Titan when they talk about leaving Earth. Almost nobody pictures it. When you picture humanity's future among the stars, you don't picture Saturn's orange moon, you picture Mars. It's worth pausing on that because it's so deeply baked into how we think that it feels less like an opinion and more like a fact of nature. Mars first, that's the consensus. The red planet is humanity's destiny, our backup, our second home, the place we'll plant a flag and build the domes and finally become a species that lives on more than one world. The moon comes up too, but usually as a stepping stone, a place to practice, a way station on the road to Mars, not really a destination in its own right. And everything else, Venus, the moons of the outer planets, Titan, those get filed under fantasy, exotic curiosities, nice to look at through a telescope, impossible to live on. The hierarchy is so settled it barely needs stating. Mars, then maybe the moon, then nothing serious. But I want to ask you a quiet question tonight, the kind of question that's best asked when you're already half relaxed and your guard is down a little. Where does that hierarchy actually come from? Why Mars first? Is it because Mars is genuinely the easiest place to keep a human being alive for a long time? Or is it because Mars is close and red and familiar, and it's been on the cover of so many books and films and dreams that it simply feels like the answer before we've even checked the question? Because when you actually check, when you set aside the familiarity and the Hollywood renderings and the century of stories, something a little unsettling happens. The settled order starts to wobble. The obvious winner stops looking so obvious. And the world almost nobody pitches starts to look on the things that genuinely matter, shockingly good. So here's what we're going to do slowly over the course of this night. We're going to take 4 worlds, 4 real, specific places in our solar system that someone, somewhere, has seriously proposed as a possible home, and we're going to score them. Not on how they look in a painting, not on how close they are, not on how they make us feel. We're going to score them on the 4 things that physics says will actually decide whether a person standing on that world lives or dies over the long term. Let me name those 4 so you can hold them loosely as we go. You don't need to memorize them. They'll come back again and again, and each time they will. The first is pressure, the weight of the air around you or the lack of it, whether the atmosphere holds your body together or lets it come apart. The second is radiation, the invisible sleet of high-energy particles streaming through space, what we call galactic cosmic rays coming from far beyond our solar system and solar particle events blasted out by our own sun. Whether the world has anything, an atmosphere, a magnetic field, anything at all, standing between that sleet and your cells. The third is temperature, simply how hot or how cold, whether you can keep yourself in the narrow band of warmth a human body insists on, or whether the world is forever trying to cook you or freeze you solid. And the fourth is resources, what's actually there on the ground or in the air that you could use. Water, breathable air ingredients, fuel, the raw stuff of survival, lying around for the taking, or not. Pressure, radiation, temperature, resources, 4 lenses, 4 worlds, and by the end of all this, a scorecard and a verdict, and I promise you the verdict is not the one you'd expect when we started. The 4 worlds, in case you're wondering, are these: Mars, of course Mars, the one everyone names, our own moon, the body we've actually walked on, sometimes called lunar, in the more poetic moments, Venus. And here I have to ask you to hold your skepticism for a little while, because Venus is going to surprise you in a way that has nothing to do with its surface. And Titan, Saturn's great golden moon, the world I opened with, the one you could, in theory, stroll across in a heavy coat. Now, before we drift gently into the first of those 4 lenses, let me hand you a little knot of curiosity to carry forward into the dark. Something to keep a tiny part of your mind turning even as the rest of you softens towards sleep. Of these 4 worlds, one of them will boil the water inside your own body the instant you step out unprotected. Not heat it, not warm it, boil it. The water in your saliva, the water in your tears, the water soaked into the soft tissue of your lungs. All of it, brought to a rolling boil at the ordinary temperature of your own warm blood. No flame required, no furnace. Just the act of stepping outside. Which world do you think it is? You might be tempted to guess the hottest one. You might be tempted to guess the coldest. Hold your guess. We'll get there. And I suspect the answer is not the one you'd reach for. Let's begin with pressure then, since it's where we started and since it's where the surprise first shows its face. You don't think about air pressure most of the time. Why would you? You were born inside it. You've never known its absence. That sky I mentioned earlier, and the entire ocean of air sitting on top of you, miles and miles of it stacked up to the edge of space. It presses on every square inch of your skin with real force, about 15 pounds, on a patch the size of a small coin, all over your body, all the time. And you don't feel a thing. You don't feel it because the pressure inside you pushes back exactly as hard. You are, in a quiet way, perfectly balanced against the weight of the world. Inside equals outside. A truce you never agreed to and never notice. But that truce only holds because there's something out there pushing back at all. Take the outside pressure away, and the inside has nothing to balance against. And your body, your soft, water-filled, sea-level body, does not respond gracefully to that. This brings us to a number and a name that I'd like you to remember if you remember anything tonight, though of course you don't have to. The number is about 6.3 kilopascals. The name is the Armstrong limit. Let me decode that gently, the way I always try to. Kilopascals are just another way of measuring pressure, like how you might measure a distance in feet or in meters, depending on who's asking. Earth's sea level pressure in those units is around 101 kilopascals, so 6.3 is a tiny fraction of what you live in, only about 6%. And the Armstrong limit is the pressure at which something deeply strange and deeply unpleasant begins to happen to liquid water. At that pressure, water boils not when it's hot, but when it's merely as warm as the inside of a human being. Around 37 degrees Celsius, body temperature. Your temperature. That's the thing that trips people up about boiling. So let me sit with it for a moment because it's lovely and a little eerie once it clicks. We tend to think boiling is about heat. You put the kettle on, the water gets hotter and hotter, and at 100 degrees it boils. But boiling isn't really about heat on its own. It's about the relationship between heat and pressure. Water boils when its molecules have enough energy to escape into the air, and the less the air is pressing down on them, the less energy they need to break free. High up a tall mountain where the air is thinner and the pressure lower, water boils at well below 100 degrees. Climbers know this. Their tea never gets quite hot enough. Lower the pressure far enough and you don't need a mountain or a stove at all. You just need the water to be lukewarm. You just need it to be alive warm.
Body warm. So now imagine a world where the air pressure sits below that Armstrong limit, below the point where body warm water boils. On a world like that, the water in your tissues isn't being held together by any outside pressure worth mentioning, and so it begins to turn to vapor inside you. The moisture on your eyes, the saliva on your tongue, the wet lining deep in your lungs, the fluids just beneath your skin.
They start to boil gently and horribly simply because nothing outside is pressing them down anymore, and they're already warm enough to escape. There's a name for that too, this boiling of the body's own fluids in low pressure. It's called ebullism, a soft word for an unsoft thing. And now I'll answer the riddle I handed you a few minutes ago. The world that does this to you, the one that boils the water in your own body the instant you step out unprotected, is not the hottest one. It's not Venus scorching down at its surface. It's not even one of the strange outer worlds, it's Mars. Mars, the red planet, the destiny world, the one everyone wants to colonize, that Mars. Because Mars, for all its romance, has almost no atmosphere to speak of. Its surface pressure averages around 6.1 millibars. Let me give you that as a fraction, because the fraction is what makes you sit up, or would if you weren't already lying down. 6.1 millibars is about 0.6% of Earth's sea level pressure, not 6%, 0.6%. The air on Mars is so thin, it barely deserves the name. And crucially, here's where the two numbers meet, that pressure sits below the Armstrong limit, below the line where body-warm water boils, which means that if you stepped out onto the Martian surface without protection, the thin pink sky overhead would do nothing to hold your body together. The water in your saliva and your tears and your lungs would begin, quite literally, to boil at your own body temperature. Ebullism, on the world we've decided, almost without thinking, is humanity's best and most obvious second home. We didn't have to guess at Mars's pressure either, by the way. We measured it again and again with the machines we've landed there. The old Viking landers decades ago, the Curiosity rover, the InSight lander with its delicate weather sensors. Every one of them carried instruments that felt the thin Martian air and reported back the same sparse number, around 6 millibars, below the line.
Mars does not hold you. Mars lets you come apart. So the planet that lives at the very top of our settlement wish list fails, and fails badly, fails catastrophically, on the very first metric we test. On pressure, Mars demands a full, sealed suit every single second you're outside, not for warmth, not for air, but simply to keep your own fluids from boiling out of you. Step outside in shirt sleeves on Mars, and you don't have minutes, you have moments.
Now hold that picture in your mind. The bulky sealed suit, the unforgiving thinness of the Martian air, the line you cannot cross. And let me walk you back to Titan, back to that golden moon, that thick, hazy sky, that surface pressure of 1.5 bar. Because the contrast is almost absurd once you lay them side by side. On Mars, the most familiar, most romanticized, most pitched destination in the entire conversation, the air is so thin it can't even keep your body's water from boiling. And on Titan, the world nobody pitches, the exotic curiosity out by Saturn that gets treated as pure fantasy, the air is actually a little heavier than Earth's own. 1.5 times the pressure you're breathing right now, more than enough to hold you together, More than enough that ebullism never even enters the conversation. So on this first lens, this first deciding question, does the world's atmosphere keep your body intact or let it fall apart? The scoreboard reads in a way that should genuinely unsettle anyone who's only ever heard Mars first. Mars. A hard fail. You die in moments without a sealed suit. Titan. A clean, almost shocking pass. You'd want to be warm and you'd need oxygen to breathe, but the pressure itself is fine. Better than fine. The pressure is a gift. And I want to slow right down here because this is the heart of what tonight is really about. And it's worth saying plainly before we drift onward. We did not pick Mars because Mars is the easiest place to survive. We picked Mars because Mars is close and because Mars is red and dramatic and has been the star of 1,000 stories, and because the human imagination got there long before the physics did. The hierarchy in our heads was built out of proximity and familiarity. It was never built out of the cold arithmetic of staying alive. When you build it out of that arithmetic instead, when you ask, simply and without sentiment, what would actually keep a person breathing and intact and warm for years on end, the obvious answer starts to come apart at the seams, the way water comes apart on Mars. The wrong target starts winning on the things that matter, and the world you'd never name begins, quietly, to look like a contender. Of course, pressure is only the first of our four, one lens out of four. And I can already feel a sensible objection forming, even in a mind that's halfway to sleep. Fine, you might be thinking, so Titan won't boil me alive the way Mars would. But Titan is out by Saturn impossibly far, drenched in cold, wrapped in air I can't breathe. Surely it fails somewhere else. Surely the universe doesn't hand you a free win like that without taking it back somewhere. And you'd be right to think so. The universe does take something back. Titan has a catch, and it's a real one, and I will not hide it from you, because the fastest way to lose your trust would be to oversell this strange orange moon and pretend it has no flaws. It has a serious flaw. We'll arrive at it. I'll lay it out honestly, the whole brutal truth of it. But here's the thread I want to leave dangling as you settle deeper into wherever you're resting tonight. 3 of our 4 worlds will kill an unprotected human being in minutes. Mars boils you. The others have their own swift ways and will meet each of them. 3 of the 4 kill you fast. The 4th one kills you slowly, and the slowness of it, turns out to be the most important thing about it. Because a problem that kills you slowly is a problem you have time to solve. And as it happens, the way the 4th world tries to kill you is the single survival challenge that human beings have been working on longer than almost any other. Longer than flight, longer than medicine. We've been solving this particular problem in one form or another since the very first time one of our ancestors gathered close to a fire and felt the warmth push back against the dark. But I'm getting ahead of myself, and there's no need to rush. There's never any need to rush here. Let that thought rest for now, half-formed, like a shape just visible across a dark room. We'll come back to it. We have all night. For now, just hold the first finding gently. The world everyone names cannot even keep your body's water from boiling. And the world no one names holds you the way home does. Pressure, the very first test, and already the familiar order has begun to turn over in its sleep. Let the rest of you go soft. We're only just beginning, and the strangest turns are still ahead. The invisible sleet of radiation, and which world has the thickest shield of all, the brutal swings of heat and cold, the question of what's actually lying around out there to keep us alive. We'll take each one slowly, one quiet mystery at a time. So breathe out. Loosen your hold on the day, and come a little further with me, out past Mars's thin pink sky, toward that golden moon and the secret still folded inside its thick orange air. Before we drift much further out, let me tell you where we're actually standing and why this question matters tonight at all. There's a story we've all been told so many times and so confidently that it's stopped feeling like a story. It feels like a fact. The story goes like this. Mars first. Mars is the destination, the second home, the backup. Then the moon, our little grey stepping stone, the place we practice before the real journey. And everything else, Venus, the moons of the giant planets, the cold outer dark, everything else is fantasy. Pretty pictures, science fiction, not for serious people. It's a tidy story, a settled one, the kind of consensus that feels so complete you'd never think to question it. And yet, like most tidy stories about the universe, it was built on the wrong things. It was built on how close a world is to us, and on how often we've seen it on a screen. Proximity and familiarity. Not on the one question that actually decides whether a human being can live there, which is simply this. What does it take to keep you alive? So tonight, let's set the familiar story gently aside just for a while and ask the harder, quieter question underneath it. If you were really choosing a second home, not for a flag or a photograph, but for a person, a body, a fragile, warm-blooded animal that needs very specific things to keep breathing, how would you actually score these worlds against each other? What would you measure? It turns out there are 4 things, 4 tests that any world has to pass before it can hold a human life. And almost everything else, all the romance and the renderings, is just decoration laid on top of these 4. The first is pressure. The simple, constant push of the air against your skin, the thing you've never once noticed in your entire life because it's always been exactly right. The second is radiation, the invisible sleet of high-energy particles streaming out of the sun and in from the depths of the galaxy, the stuff our own thick air and magnetic field quietly turn aside for us every second of every day. The third is temperature, whether a world will cook you or freeze you or simply let you be. And the fourth is resources, whether there's anything out there lying around in the dirt or the air or the ice that you could actually use to make water and air and fuel and a life. Pressure, radiation, temperature, resources. Hold those 4 words loosely. You don't need to memorize them. They'll come back one at a time, slow and gentle, like guests arriving for a long, quiet evening. We'll spend the whole night with them. And here's the thing that turns the familiar story over. When you actually score the worlds on these 4, really score them, with the physics and not the poetry, one of them, the one almost nobody ever pitches, passes 3 of the 4 tests with room to spare. And the famous one, the one everyone's already half-packed for, fails 2 of the hardest tests of all. But let's not leap to the end. Let's start where we always should, with the very first test, the gentlest one, pressure. Now, before we go any further, wherever you are right now, tucked under a blanket, lying in the dark with one lamp still glowing somewhere, maybe on a train rocking gently through the night, settle in properly. You don't have to follow every number. You don't have to remember a single one of them by morning. If you drift off somewhere over Mars and wake up out near Saturn, that's perfectly fine. The worlds will still be here. I'll still be here. The whole point of these slow journeys is that you're allowed to let go. And if you'd like more nights like this one, more long, slow wanders out past the planets, a quiet like and subscribe genuinely helps. This is a small channel, and small creators like me really do rely on it to keep going. To everyone already here with me, already part of this, thank you, truly. So tell me, before you drift, where in the world are you watching from tonight? What time is it? In your corner of the dark? I always love knowing how far this little signal travels. Right, settle back. Let's begin where every survival story begins, with the air itself and the pressure it carries. You don't feel it, but right now there's an ocean pressing on you. The whole weight of the atmosphere, kilometers of air stacked overhead, leaning down on every inch of your skin at about 1 bar of pressure. 1 atmosphere. Your body was built inside that push. Every cell of you is balanced perfectly against it, pressing out as hard as the air presses in. A quiet truce you've never had to think about. It's the most invisible comfort there is. Now take that comfort away and you start to understand what space actually does to a body. Begin with the famous one. Begin with Mars, the red world, the destination, the second home of 1,000 bright renderings. Mars does have an atmosphere, and that's part of what makes it feel so reachable, so nearly livable. There's a sky there, there are sunsets, a strange, dusty blue at the close of the day. There's weather and wind and seasons. But that atmosphere is a ghost of one. The air pressure at the surface of Mars averages about 6 millibars, 6,000ths of a bar, less than 1% of what's pressing on you right now. To stand on Mars in that thin air is, as far as your body is concerned, to stand in something almost indistinguishable from a vacuum, and here's where it stops being an abstraction and starts being about you. There's a threshold, a particular pressure, with a name, the Armstrong limit. It sits at around 63 millibars, about 6.3 kilopascals. And below that line, something quietly horrifying becomes true. Below the Armstrong limit, water boils at the temperature of the human body. Not boiling hot water on a stove. The water that is already inside you, right now, at your own gentle warmth. Your saliva, the film of moisture across your eyes, the wet lining of your lungs. Below that line, all of it begins to turn to vapor. Mars, at 6 millibars, sits far, far beneath the Armstrong limit, not a little under, roughly 10 times under. So step out onto the Martian surface unprotected, and the water in your mouth and your eyes and your tissues would start to bubble and boil at body heat. The medical name for it is ebullism, and it's exactly as unkind as it sounds. The world everyone wants to settle, the obvious choice, the safe bet. Its very air would boil you from the inside out the moment you took off your helmet. That's the first test, and the famous one fails it completely. Now hold that and let me take you somewhere else, far out. Past the asteroids, past Jupiter, almost 1.5 billion kilometers from the Sun, to a small orange world wrapped in a thick golden haze. Saturn's largest moon, Titan. And here is where the familiar story begins to turn over in its sleep. Because Titan has air too, sire, but not a ghost of an atmosphere. A real one, a deep, dense, heavy blanket of it. The pressure at Titan's surface is about 1.5 bar. Read that again, slowly. 1.5 bar, that's not a fraction of Earth's pressure, that's more than Earth's pressure. About 1.5 times the ocean of air you're breathing right now. We know this number not from a model or a guess, but because we sent something there to feel it. In 2005, a small probe called Huygens, built by the European Space Agency, rode all the way out aboard the Cassini spacecraft and parachuted down through Titan's orange haze, measuring the air the whole way down. It touched the surface and it told us plainly, the pressure here is survivable. Comfortable even. Think about what that actually means for a body. On Titan, you would need no pressure suit, none. No bulky armored shell holding the vacuum off your skin because there is no vacuum. There's a thick, gentle earth and then some weight of air pressing on you, the same kind of push you felt every moment of your life. The water in your body would stay exactly where it belongs. You'd need warmth, yes. We'll get to the cold, and it's real. and you'd need something to breathe because there's no oxygen in that air. But picture the gear. A heated parka, thick and well insulated. A mask feeding you oxygen. And that more or less is it. It's almost exactly the setup of a cold weather scuba diver, wrapped against the chill, carrying your own air, but otherwise just standing there in the open on the surface of another world.
No pressure suit. On the moon no one ever names, while the world everyone's already packing for would boil you alive. Pressure. The very first test, the gentlest one, and already the familiar order has begun to quietly turn over beneath us. So let's press on, because pressure is only the beginning.
There are 4 things that will kill an unprotected human being in space, and we've met the first one, but the second one is arguably worse. Not because it kills faster, though sometimes it does, but because it's invisible. You can't feel it arriving, you can't hold your breath against it. It passes right through you, through the walls of your habitat, through anything short of a substantial thickness of mass, and it's damaging your DNA quietly, patiently, the entire time you're exposed to it.
Radiation. And this is where the comparison gets genuinely strange, because the world that loses so badly on pressure, the world where the air is so thin it can't hold your bodily fluids together, also loses on this second metric. And the world that surprised us on pressure is about to do something even more unexpected.
Let's start with Mars, because Mars is where most of the conversation goes, and because it's where the radiation story is most thoroughly documented. We don't have to guess here. We have a machine sitting on the Martian surface right now, the Curiosity rover, which has been rolling across Gale Crater since 2012, and it carried an instrument called the RAD, the Radiation Assessment Detector. Scientists led by Don Hassler published the findings in the journal Science in 2014, and what they measured was this. The surface of Mars receives roughly 0.7 millisieverts of radiation per day. Now, a millisievert is a unit of biological radiation dose. It's not just measuring how much radiation is there in the abstract, it's measuring how much damage that radiation represents to living tissue. And 0.7 millisieverts per day might sound small. Let's make it concrete. The career radiation limit for an astronaut set by agencies trying to keep long-term cancer risk within a manageable range is somewhere around 1,000 millisieverts over a lifetime of spaceflight. Some estimates put acceptable career limits a little higher, some a little lower, but that's the rough region of the conversation. At 0.7 millisieverts per day on the Martian surface, you would exhaust a career radiation dose in approximately 500 days, a year and a half, a little under 17 months of standing on Mars, breathing your bottled air, doing your work, and you've spent what was meant to be a lifetime's safe allowance of radiation exposure. And that's assuming a quiet period, with the sun behaving itself. The radiation arrives in 2 main streams. One is galactic cosmic rays, GCRs, the physics community calls them, which are high-energy particles accelerated by supernovae and other violent events across the galaxy, traveling at a significant fraction of the speed of light, streaming in from all directions. They're there all the time, like a constant hiss of particle bombardment. The other is solar particle events, eruptions from the sun, coronal mass ejections that fling charged particles outward in sudden storms that can dramatically spike the dose rate for hours or days at a time. Earth is protected from both of these. We have 2 layers of defense that we almost never think about because we've never had to live without them. The first is our magnetic field, a planet-wide invisible shell generated by the churning of molten iron in Earth's core, which deflects charged particles away from the surface, guiding them toward the poles and preventing them from reaching most of humanity. The second is our atmosphere, a column of air roughly 10 kilometers deep at its useful lower portion, substantial enough that particles lose energy passing through it, arriving at the surface already diminished. Mars has neither of these in any meaningful form. Mars lost its global magnetic field billions of years ago when its core cooled and solidified and stopped generating the currents needed to sustain it. There are local remnant magnetic anomalies in the crust, patches of ancient magnetism, fossils of a planet that once had something like a protective field. But they're scattered and partial, they don't form a coherent shield. And the atmosphere, as we've established, is those 6.1 millibars, a veil so thin it barely registers as air. It cannot stop what's coming down from above, and so the radiation arrives at the surface of Mars largely unimpeded. Galactic cosmic rays that have been traveling for thousands of years across interstellar space, arriving at your habitat's outer wall with almost nothing to slow them down. Solar storms that would be a beautiful aurora display on Earth become, on Mars, a genuine emergency. Settlers would need radiation storm shelters, buried structures or rooms surrounded by enough mass to absorb the worst of a solar particle event before the dose gets dangerous. Water is actually an excellent radiation absorber, so is regolith, but you'd need to be inside fast when the alert came. This is not a hypothetical concern being raised by overcautious scientists. The RAD instrument measured it directly. The Hassler et al. Paper is real, the numbers are documented, and the engineers designing every serious Mars mission concept wrestle with it constantly. The radiation is one of the hardest problems Mars poses. Perhaps harder, in some ways, than the pressure problem, because the pressure problem has a clear engineering solution. Build a strong enough suit or habitat. Radiation at the doses Mars delivers is a slow biological accumulation, and the only reliable defense is either mass, lots of it between you and space, or time, meaning you leave before you've accumulated too much. Neither of those is a comfortable answer for a permanent settlement. Now let's walk over to the Moon, because the Moon is often positioned as the easy starting point. Just 3 days away, proven that humans can land there, useful as a training ground and a logistics base. And on pressure, the Moon is a flat loss. No atmosphere at all, essentially a perfect vacuum, about 3 times 10 to the negative 15th bar of extremely tenuous gas, barely enough particles to count. You need a full pressure suit every moment you step outside. That was already established. On radiation, the Moon is worse than Mars. There's no atmosphere to absorb anything. The cosmic rays and solar particles arrive directly at the surface, attenuated by nothing, and the Moon has no global magnetic field either. It has some weak local anomalies, similar to Mars, but nothing like a coherent magnetospheric shield. Astronauts on the lunar surface during Apollo missions received radiation doses, and while those short visits stayed within acceptable limits, the picture for long-term habitation is far more concerning. We now have direct measurements from the surface that post-date Apollo. China's Chang'e-4 lander, which came to rest on the far side of the Moon in January 2019, carried an instrument called the LND, the Lunar Lander Neutron and Dosimetry Instrument, built by Kiel University in Germany. In 2020, scientists published the LND measurements, and they found that the radiation dose rate on the lunar surface is roughly 1.3 times the equivalent dose rate measured on the International Space Station. Think about that for a moment. The ISS, orbiting at 400 kilometers altitude, is already outside the bulk of Earth's protective atmosphere. Astronauts on the ISS receive elevated radiation compared to people on the ground, and the Moon's surface is getting significantly more than that. During solar particle events, the dose rate spikes far higher, with no shelter available short of going underground or hiding under many meters of regolith. The Moon is, from a radiation standpoint, a hostile open plain with no cover. Long-duration lunar settlements would need to be substantially buried or built inside lava tubes, natural tunnels in the lunar subsurface created when lava flows solidified on the outside while still liquid inside, leaving hollow channels. These would provide excellent radiation shielding from the rock above. There's active scientific interest in locating and characterizing lunar lava tubes for exactly this reason. But it's an additional engineering challenge, an additional constraint, and it underscores that the Moon's surface itself is not a friendly environment for unprotected biological tissue over extended periods. Venus now. We need to make a careful distinction here because Venus is two completely different stories depending on where you're talking about. At the surface of Venus, and we have data from Soviet probes that actually landed there, the Venera series, in the 1970s and 1980s, which were extraordinary pieces of engineering that lasted somewhere between 23 minutes and about 2 hours before the environment destroyed them. The surface pressure is 92 bar. To give you a sense of what 92 bar means to a human body, the pressure at about 900 meters beneath the surface of Earth's ocean is in that neighborhood. If you've ever thought about what diving to extreme depths does to the human body, the pressure on Venus's surface is in that regime. It would crush an unshielded person instantly. There is no suit design that makes a human standing on the Venusian surface plausible with anything close to current technology. And even if you could withstand the pressure, the surface temperature is around 465 degrees Celsius, hot enough to melt lead. The atmosphere is mostly carbon dioxide, the clouds rain sulfuric acid, and the whole system is a genuinely perfect mechanism for destroying organic life. But we're not talking about the surface of Venus. There is a concept called HAVOC, the High Altitude Venus Operational Concept, developed by researchers at NASA Langley, which identifies a very different environment roughly 50 to 55 kilometers above the Venusian surface, floating in the upper cloud decks. At that altitude, the pressure is approximately 1 bar. Earth normal. Not almost Earth normal, not close. 1 bar, the kind of pressure you're feeling right now wherever you're resting. And the temperature at that altitude ranges from roughly 0 to 50 degrees Celsius. A range that includes a perfectly comfortable shirt-sleeve environment. This is one of the more quietly astonishing facts in the solar system, honestly. The planet universally known as the closest thing to hell that our neighborhood contains, the world of crushing pressure and acid rain and temperatures that melt metal. That same planet, if you go to the right altitude, has conditions that bracket what you'd find on a pleasant spring afternoon in many of Earth's cities. On radiation, the cloud deck at 50 kilometers offers real shielding from above. The thick atmosphere of Venus, all those tens of kilometers of gas above you, absorbs and scatters radiation the way a thick atmosphere should. Venus lacks a magnetosphere, so it doesn't have the magnetic deflection that Earth has, but the atmospheric column above the cloud decks provides substantial attenuation of incoming radiation. It's less studied than Titan's shielding, and the absence of a magnetosphere is a genuine gap in the defense, but it's significantly better than what the Moon or Mars offers. The catch on Venus, and there's always a catch, is that you are in the clouds. The clouds that, in Venus's case, are made of concentrated sulfuric acid. A habitat at 50 kilometers altitude is floating in a corrosive chemical environment. Any hull breach isn't a vacuum event, or you're not going to lose pressure into emptiness. It's a chemical event. The acid eats through materials, damages exposed surfaces, and any system exposed to the cloud environment needs to be acid-resistant in ways that current spacecraft materials are only partially designed for. And you have no ground under you. There is no surface to build on, no regolith to mine, no bedrock to anchor to. You float. And if something goes wrong with your buoyancy or your structure, you fall, and you fall through increasingly hotter, denser atmosphere until the pressure and temperature end the matter. There's a particular kind of exposure there, not to vacuum or cold or radiation in the acute sense, but to a chemical environment that degrades your habitat from the outside continuously, requiring constant maintenance of your acid-resistant surfaces. And the fundamental lack of any solid ground, any material to mine and build with, any anchored foundation, sets a ceiling on what Venus's cloud decks could realistically host. So, On radiation, Venus's cloud decks do reasonably well, not as well as we're about to discover, but better than the Moon, better than Mars's exposed surface, and with a thickness of atmosphere above providing real protection, which brings us to Titan. And this is the moment in the comparison that genuinely surprised researchers when they ran the numbers carefully, because it's counterintuitive in a way that takes a moment to settle. Titan's atmosphere is extraordinary. We knew before Huygens that Titan had an atmosphere. It had been observed to have one. It was why Titan appeared as an opaque orange sphere rather than a surface-visible world when Voyager flew past. But what Huygens and Cassini revealed in full was the scale of it. Titan's atmosphere, in terms of column mass density, with the amount of mass sitting above each square meter of surface pressing down, is roughly 10 times more massive per unit area than Earth's own atmosphere. 10 times. Let that drift in for a second. Earth's atmosphere provides excellent radiation shielding. It's part of why surface radiation on Earth is so much lower than the radiation environment in orbit. We don't usually think of the air above us as protective armor, but it is. It's a 10-kilometer thick ocean of gas that charged particles have to fight their way through before they get to us, and most of them don't make it in their original high-energy form. And Titan's atmosphere, column for column, has 10 times as much mass. This makes Titan's surface the most thoroughly radiation-shielded solid surface in the solar system. Not in the inner solar system, in the entire solar system, no moon, no planet has a thicker atmospheric radiation shield over a surface you can stand on. Earth's own surface gets more radiation than Titan's. And there's another layer to this. Saturn, the giant ringed planet that Titan orbits, has a magnetosphere of its own, generated by Saturn's rapid rotation and its interior. When Titan is inside Saturn's magnetosphere, which it is for a significant portion of its orbit, the charged particles that might otherwise reach Titan's upper atmosphere are deflected by Saturn's magnetic field before they even get that far. So Titan has not just one shield, 10 times Earth's mass atmosphere, but periodically a second shield, Saturn's planetary magnetosphere, a vast bubble of protected space that Titan passes through. The combination is remarkable. A settler on Titan's surface would receive a radiation dose that is, by the best measurements and models we have from the Cassini mission, extremely low. Not just lower than Mars, not just lower than the Moon, genuinely, significantly lower in a way that would not impose the kind of career-limiting countdown that Mars imposes, or the shelter-seeking emergency calculus that solar storms create on the lunar surface. The implications are worth turning over slowly because they're counterintuitive in the context of how we normally discuss these destinations. When people talk about Mars as the next home for humanity, radiation is usually framed as a serious but manageable engineering problem. You build your habitats underground, or you cover them with regolith, or you develop better pharmaceutical countermeasures, or you accept elevated cancer risk as the price of being pioneers. These are real discussions happening in real planning documents. The problem is acknowledged. What isn't usually mentioned in those discussions is that there exists a world in the outer solar system where you don't have to have that discussion at all, where the atmosphere itself has done the engineering for you, where a settler on the surface is better protected from radiation than a person sitting on Earth's surface would be, not because of any technology they brought with them, but because of simple, massive, natural atmospheric shielding. We sent a probe to measure it. Cassini, that extraordinary joint mission between NASA, the European Space Agency, and the Italian Space Agency, which orbited Saturn from 2004 until its planned atmospheric plunge in 2017, spent 13 years observing Titan's environment in extraordinary detail. Huygens, built by ESA and released from Cassini on Christmas Day 2004, arrived at Titan on January 14, 2005, and descended for 2 hours and 27 minutes through the atmosphere before landing and continuing to transmit for another 72 minutes on the surface. That mission gave us the pressure number, 1.5 bar, and it gave us the atmospheric composition, and it gave us the temperature. Cassini's years of observation gave us the atmospheric column mass, the interaction with Saturn's magnetosphere, the nature of the surface. These aren't extrapolations or models built in the absence of data. They're observations. So now let's step back for a moment and draw the first 2 rows of our scorecard, because it helps to have the picture in front of us even if we're just carrying it in our heads. On pressure, Titan passes with something approaching a gold star, 1.5 bar, no pressure suit required, the most hospitable surface pressure after Earth and the cloud decks of Venus. Mars fails at the level of biological crisis, 6.1 millibars, below the Armstrong limit, ebullism, the water in your body trying to become a gas. The Moon fails more completely, essentially no atmosphere at all. Venus at the surface fails catastrophically at 92 bar. Venus at the cloud decks passes, sitting right at 1 bar. On radiation, Titan takes first place, not just among our 4 candidates, but in the entire solar system for solid surfaces. 10 times Earth's atmospheric column mass, plus periods inside Saturn's magnetosphere, delivering radiation levels that would give a long-term settlement no particular radiation management crisis to solve. Venus's cloud decks take second place, real atmospheric shielding from above, meaningful attenuation, though the lack of a magnetosphere is a gap. Mars is a distant third, measured directly by Curiosity's Radi instrument, 0.7 millisieverts per day, a career limit exhausted in roughly 500 days, requiring underground habitats or storm shelters to make long-duration stay survivable. The Moon comes last. No atmosphere, no magnetosphere. 3 times the ISS dose rate from Chang'e-4's LND measurements in 2020, demanding burial or lava tubes for any long-term residents. 2 metrics in. And the picture is already different from the one most people are carrying around. But let's keep going, because we still have 2 more metrics to walk through, temperature and resources. And one of them is where Titan hands you back the problem, the one real obstacle on its surface, the thing that makes this whole comparison genuinely complicated rather than a simple declaration of a winner. And the other metric is where some of these worlds reveal resources that could make a settlement actually function over decades and generations rather than just survive for a short stay. Before we get there though, let's complete the pressure picture on 2 of our candidates, because it deserves a full accounting. The Moon's pressure situation is as stark as it gets, 3 times 10 to the negative 15th bar, a figure that has no intuitive meaning. So let me give you one. If you took a cubic meter of the Moon's surface atmosphere and compressed it down to the conditions of Earth's sea level, you'd have a volume so small it would be essentially invisible, a handful of molecules. The Moon's atmosphere is sometimes called an exosphere, the outermost, most tenuous trace of gas that a body can hold, barely clinging against the bombardment of solar wind that's constantly knocking molecules loose and sending them into space. There is, for all practical purposes, no atmosphere on the Moon. Every moment you spend on the Moon's surface, without exception, you are one failure away from the same pressure problem that Mars presents, but without any margin at all. On Mars, if something goes wrong with your suit and you lose pressure, you have a few seconds before ebullism begins. On the Moon, the situation is identical, but there's not even a trace of ambient gas to push back. The engineering challenges of the pressure suit, the airlock, the habitat integrity are all mandatory and absolute, with no atmospheric assistance whatsoever. The permanently shadowed craters at the lunar poles, regions that haven't seen sunlight in billions of years, are where the Moon's water ice is concentrated, delivered over eons by cometary impacts, and preserved in the eternal cold. The L-Cross mission, a clever 2009 experiment where NASA deliberately crashed a rocket stage into one of these craters and analyzed the plume with a following spacecraft, confirmed water ice is there. That ice is an important resource and we'll return to it. But from a pressure standpoint, those craters are also among the coldest natural environments in the solar system, down near 40 Kelvin above absolute zero in the deepest permanently shadowed regions, which the Diviner instrument aboard the Lunar Reconnaissance Orbiter has mapped. Even outside those craters, the lunar surface experiences enormous thermal swings, but let's save temperature for the next part of the story. For Venus, the pressure accounting is worth dwelling on a moment longer because it's so dramatically split. At the surface, 92 bar. The number is so large it's almost abstract, so let me give it a body. At Earth's ocean surface, pressure is 1 bar. Each 10 meters of ocean depth adds roughly another bar. To reach 92 bar in Earth's ocean, you'd need to descend to about 900 meters, the depth that was only reached by specially designed submersibles, the kind with thick titanium spheres and extreme engineering to prevent the ocean from crushing them. The Venusian surface offers that same pressure, except instead of cold, dark water, it's 465-degree carbon dioxide. The Soviet Venera probes that actually made it to the surface were extraordinary feats of engineering, essentially designed as armored capsules that could survive just long enough to take some measurements and transmit before the environment destroyed them. Venera 13, which landed in 1982, lasted 127 minutes before going silent. That's the longest any human-made object has operated on the Venusian surface. 127 minutes. But at 50 to 55 kilometers altitude, that's the figure to hold on to, the pressure is approximately 1 bar. Earth normal. This is a consequence of simple atmospheric physics. Pressure drops with altitude as there's less gas above you pressing down. Venus's atmosphere is so massive that by the time you've climbed 50 kilometers into it, you've left behind enough of it that what remains above is roughly the same column as Earth's atmosphere at sea level. And the temperature at that altitude is between approximately 0 and 50 degrees Celsius. The HAVOC concept from NASA Langley identified this zone explicitly, the high-altitude Venus operational concept, and proposed that this might be a viable environment for human presence in the form of large, buoyant habitats, essentially dirigibles floating in that temperate Earth pressure layer above the worst of the acid and below the upper atmosphere. The radiation shielding at that altitude is provided by the tens of kilometers of thick Venusian atmosphere above. All that gas, all that mass, standing between you and the incoming cosmic rays. It's less well characterized than Titan's shielding, partly because we've had instruments specifically designed to measure it on Titan from Cassini and less complete measurements for Venus at altitude. But the basic physics is sound. A thick atmosphere absorbs radiation. Venus's cloud deck is under a substantial atmospheric column. The catch, as mentioned, is structural and chemical. You're floating in sulfuric acid clouds, not near them, not drifting over them, inside them. The acid concentration in Venus's clouds, measured by the Soviet and American probes of the 1970s and 1980s, is roughly 75 to 96% sulfuric acid by mass. This is concentrated industrial-grade acid, the kind that would destroy most metals, most polymers, most materials you'd normally build a habitat from. A cloud city on Venus would need to be made of materials that are acid-resistant, which exists, certain grades of PTFE, certain ceramics, fluorinated polymers, but it adds a layer of materials constraint that Mars and Titan don't share. And the floating nature of the habitat is its own kind of vulnerability. A solid foundation gives you something to anchor to, something to build from, a stable surface to land vehicles on, a place to store things underground, a substrate to mine. When you're floating, you are entirely dependent on your buoyancy system. If that system degrades or fails, there is no emergency ground to land on. The surface below is not a survivable destination under any circumstances. You fall, and falling on Venus is a one-way commitment. None of this makes Venus's cloud decks impossible as a concept. The HAVOC analysis concluded it was genuinely worth considering, and the pressure and temperature at that altitude remain some of the most Earth-like conditions in the solar system. But it underscores that each of our 4 candidates, even the ones that do surprisingly well on certain metrics, bring their own suite of engineering demands. The challenges just differ. On the Moon and Mars, the challenge is the fundamental hostility of the environment to biological tissue. On Venus's cloud decks, the challenge is more structural: the acid, the floating, the lack of surface access. And on Titan, and we're approaching this, we're nearly there, the challenge is thermal, just thermal, which, when you've spent this much time thinking about pressure that boils your blood and radiation that eats your DNA and acid clouds and surface pressures that crush metal capsules in 2 hours, cold starts to feel like a very particular kind of problem, a solvable kind. But let's not rush toward it. The numbers deserve to be heard. 2 metrics down. Pressure, Titan at the top, then Venus cloud decks, then failing grades for Mars and the Moon in different directions of wrongness. Radiation, Titan again at the top, Venus cloud decks second, Mars third, with documented career limit concerns, Moon last with measured dose rates exceeding the ISS and no atmospheric shelter. A pattern is forming, and the pattern is not what most people would have predicted when they started this comparison. It's not Mars at the top, it's not Mars in second. Mars is sitting in 3rd or 4th place on the metrics we've covered so far, the very metrics that determine whether an unprotected human being survives the first hour, the first year, the first decade. The world with the most active settlement plans, the most cultural momentum, the most engineering effort, the most public enthusiasm, Mars is not winning this comparison. And the world sitting quietly at the top of both columns. An orange moon of Saturn, 1,400 million kilometers from the Sun, a place that most people, when asked to name the second home of humanity, would not name, is Titan. 2 down, 2 to go. So, temperature. This is the one. This is the metric where Titan stops looking like a surprise winner and starts looking like it has a problem. A real, serious, undeniable problem. And if we're doing this comparison honestly, we don't get to soften it or bury it or wave it past in 3 words. 94 Kelvin. That's Titan's surface temperature. 94 Kelvin, which translates to negative 179 degrees Celsius, or if you're more comfortable in Fahrenheit, negative 290 degrees. And I want you to sit with that number for a moment, wherever you are, whatever is warm around you right now. The blanket, if you have one, the heat coming through the window, the quiet background warmth of a room with walls and a roof, and insulation between you and the outside. All of that is doing something very specific. It is keeping you at roughly 310 Kelvin, and Titan's surface is at 94. That gap, more than 200 degrees of Kelvin between a comfortable human body and the ground it's standing on, is Titan's decisive challenge. It is not a small engineering task. It is not something you solve with an extra sweater. But here's the thing, and this is the reframe that the rest of the temperature section turns on, so stay with it. Cold is a specific kind of problem. When we went through pressure, we were talking about forces that act on the human body in ways that are nearly impossible to counteract with portable technology. At Mars's 6 millibar surface pressure, the water in your tissues doesn't need a heat source to boil. It just boils because the pressure threshold that keeps liquid water liquid in living tissue is not being met. The Armstrong limit isn't a suggestion, it's a physical law. And no amount of insulation or engineering workaround changes the fact that below roughly 63 millibars, the human body at body temperature will experience ebullism. The only solution is to contain a higher pressure environment around the person, which is a full pressure suit, always, every time, no exceptions. Any breach is immediately life-threatening. When we went through radiation, we were talking about ionizing particles moving at significant fractions of the speed of light, able to pass through most materials, disrupting DNA, raising cancer risk, accumulating in the body invisibly over time. Shielding against galactic cosmic rays requires enormous mass, meters of water or regolith or specialized polymer, and the doses we measured on Mars's surface with Curiosity's RAD instrument, about 0.7 millisieverts per day, can't be engineered away at the surface level without infrastructure that doesn't yet exist. The atmosphere Mars has is not enough. The magnetosphere Mars has is not enough. There isn't one. Those are hard problems. Not impossible, but hard in the way that means the engineering required is fundamentally unusual. You are fighting against invisible particles and against the vacuum of space itself and against the nature of a planetary body that doesn't offer you shelter. Cold is different. Humans have been solving cold for as long as humans have existed. We discovered fire, we built shelter, we wore animal skins and wove fabrics and piled stones and built fires inside stone rooms and invented central heating and then eventually invented the insulated foam panels and electric heating elements and thermal management systems that let us function at ambient temperatures that would kill an unprotected person in minutes. We solved Antarctica. We solved Siberia in winter. We solved the inside of a freezer, the inside of a cryo chamber, the inside of a spacesuit on the moon where the temperature in permanent shadow drops to near absolute zero and astronauts worked in it. Cold kills slowly. That's the crucial distinction. Hypothermia is a gradual process. A person exposed to severely cold air does not instantly cease to function. The body fights, the core temperature drops over time, and critically, that process can be interrupted. A person exposed to vacuum experiences ebullism in seconds. A person exposed to acute high-dose radiation may not feel the effects immediately, but the cellular damage is done in the moment. Cold gives you time, and time is what engineering needs to work with. More than that, the technology to maintain warmth in extreme cold environments already exists. It is not theoretical. It is not decades away. We have nuclear reactors. We have radioisotope thermoelectric generators. The same RTG technology that has been powering spacecraft in the outer solar system for decades, that powered Cassini on its journey to Saturn, and then its years in orbit around Saturn, that powered the Voyager probes and the Pioneer probes and Curiosity on Mars. An RTG produces heat as a byproduct of its electricity generation. Constant, reliable, not dependent on sunlight, not dependent on anything other than the slow decay of a radioisotope. And on Titan, we'll come to this properly in a moment, the energy source you would need anyway, for reasons we'll get to, produces exactly the waste heat you need for exactly the thermal management problem you have. There is a beautiful symmetry in that once you see it. But first, the whole temperature table. All four worlds. Mars. The world where the thermal story sounds, at first, almost reasonable. Mars has actual seasons. Mars has a day almost exactly as long as Earth's, 24 hours and 37 minutes, give or take. Mars has equatorial regions where, at local noon in summer, the surface temperature can reach positive 20 degrees Celsius. That's above freezing. That's the temperature of a mild spring day. If you were standing on the Martian equator at high noon in summer, the temperature reading alone would not seem alarming. But the range, the brutal, uncompromising range of Martian temperatures is the part that makes the spring day moment almost misleading. That same Martian surface that touched positive 20 at noon will drop to negative 125 degrees Celsius or colder before the night is out. At the poles, temperatures dive below negative 125 routinely. The average surface temperature across all of Mars, all latitudes, all seasons, is approximately negative 63 degrees Celsius. Not the pleasant noon hour snapshot, negative 63 as the mean. And the thin atmosphere, the 6 millibar atmosphere that already failed the pressure test so catastrophically, means that the air itself doesn't hold or transfer heat effectively. Thick air cushions temperature swings. It stores thermal energy, redistributes it, moderates the extremes. Mars's atmosphere is too thin to do this well. The temperature swings are large, they're rapid, and the thermal gradient from the sunlit surface to just a few meters above it can be dramatic. There are dust devils, genuine, spinning columns of electrified dust, and they form partly because of how rapidly the surface heats relative to the air above it on that thin atmospheric layer. So Mars gives you a temperature range you can survive, technically. The numbers don't immediately kill you the way Titan's 94 Kelvin does, but the engineering challenge of surviving Mars thermally is not trivial either, because you are designing for a swing of more than 140 degrees Celsius between noon and night, and you're doing it in an environment where your pressure suit is already dealing with maintaining internal pressure against a near-vacuum exterior, which makes adding robust thermal management more complex, more weight, more potential failure modes. Mars's thermal story is survivable but demanding, not a simple win. The Moon. This is where the temperature picture becomes, in some ways, the starkest outside of Titan. The Moon has almost no atmosphere at all, roughly 3 times 10 to the power of negative 15 bar, which is essentially the same as saying there is nothing there in any meaningful atmospheric sense. And the consequence of having no atmospheric buffer is that the Moon experiences some of the most extreme surface temperature swings in the inner solar system. During the lunar day, which lasts about 2 Earth weeks because the Moon rotates so slowly, the sunlit surface can reach positive 120 degrees Celsius. Then the lunar night arrives, also about 2 Earth weeks, and those same sunlit plains fall to negative 170 degrees Celsius, a swing of nearly 300 degrees Celsius between day and night over the course of what amounts to a month. The Lunar Reconnaissance Orbiter's Diviner instrument has been mapping these temperatures with precision, and one of the things Diviner found, one of the things that has made the lunar South Pole increasingly interesting to mission planners, is the permanently shadowed regions. Craters near the poles that never, due to the Moon's axial tilt, receive direct sunlight. In those craters, Diviner measured temperatures approaching negative 240 degrees Celsius. Nearly as cold as Titan, colder in fact than Titan, in the most extreme shadowed pockets. And unlike Titan, where the cold is uniform and predictable and therefore something you can design around, the Moon gives you enormous thermal cycling stress. Materials expand and contract with temperature. Seals flex and fatigue. Solar panels work beautifully during the 2-week day and produce nothing during the 2-week night. A lunar base has to survive not just cold, but the repeated shock of going from very hot to very cold and back again every month, indefinitely. That's a materials engineering and power systems challenge that is genuinely different from Titan's challenge of simply staying warm all the time. Titan is cold. The Moon is chaotically, cyclically violent in its temperature behavior. Venus cloud decks, this is where the temperature story does something remarkable. At 50 to 55 kilometers above Venus's surface, the altitude range that the HAVOC concept from NASA Langley has explored as a potential human habitat zone, the temperature sits between approximately 0 and 50 degrees Celsius. Depending on the exact altitude within that band, you might find temperatures between about 20 and 30 degrees Celsius, which is, to be plain about it, genuinely comfortable for a human being, not requiring any particular thermal management beyond what you'd need for a building or an enclosed vehicle. The temperature outside the habitat isn't trying to freeze you or cook you. It's just there like a somewhat warm day, floating above the most hellish surface in the solar system. The Venera probes that reached Venus's surface found temperatures around 465 degrees Celsius, hot enough to melt lead, driven by the most extreme greenhouse effect in the solar system. The Pioneer Venus mission confirmed the surface picture. And then 50 kilometers above that inferno, you find something that sounds almost impossible. Temperatures where humans live comfortably, pressures close to Earth's sea level, and gravity nearly identical to Earth's. Venus's cloud decks win the temperature comparison outright. They are the only off-Earth environment in this comparison where the ambient temperature requires no special thermal management at all. But, and this but is very large, those clouds are concentrated sulfuric acid. We touched on this when we were going through the pressure comparison earlier, and it's worth naming it again here in the temperature section because it shapes everything about what Earth-like temperature means in practice at Venus 50 kilometers up. The environment around your habitat is not air you can briefly tolerate. It is a chemical that would dissolve your lungs and burn through most conventional materials. The hull of anything you build up there has to be chemically resistant in ways that add complexity, add weight, add maintenance burden, with no possibility of resupply from below and no surface to land on if something goes wrong. You are permanently floating. The only direction that isn't hostile is inward into your habitat. Earth-like temperature in an acid cloud is not the same thing as Earth-like temperature in clean air. The number is right, the context makes it complicated. So, the temperature table. Venus cloud decks win on the number alone, with the enormous asterisk of sulfuric acid and no solid surface. Mars is survivable but demanding, with a wide swing and a thin atmosphere aggravated thermal environment. The Moon has extreme cycling and shadowed craters colder than most of the outer solar system. And Titan is simply, uniformly, relentlessly cold. Negative 179 degrees Celsius, all the time, everywhere, as a condition of existing on its surface. Titan loses the temperature column on the raw number, but, and this is the reframe that matters, it loses it in the most manageable way of the bad options. The cold is constant, which means you design for a single known condition rather than cycling extremes. The cold is the same everywhere, which means your habitat design is consistent. And the technology to produce heat, nuclear specifically, in the form that was already proven on the Cassini mission that gave us all of these Titan facts. That technology already exists and has been tested in the outer solar system environment where it needs to work. There is one more thing about Titan and cold that needs saying here, something that will come back when we get to resources. When you are generating heat from a nuclear power source on Titan, you are not solving two problems. You are solving one problem twice with the same solution. The reactor that powers your lights and your oxygen recyclers and your communications equipment produces waste heat. That waste heat, on most applications in space engineering, is a problem to be managed. You have to get rid of it somehow, usually through radiators. On Titan, that waste heat is precisely the warmth you need. The thing that's a nuisance to dispose of on a spacecraft in the inner solar system is your heating system on Titan. The engineering problem and the engineering solution are the same physical process. We will come back to this. But let's stay in order. Resources, because this is where the comparison shifts again, and this is where, if you've been keeping a mental scorecard, you are about to update it one more time. Resources. What does each world actually offer a settlement that wants to stay? Let's start with the Moon, because it's the closest and the most honestly mixed picture. The Moon has water ice. This is now confirmed, and it matters enormously. L-Cross, the lunar crater. Observation and sensing satellite impacted a permanently shadowed polar crater in 2009, and the resulting debris plume showed water ice present in the regolith at the lunar poles. Chang'e missions have continued to build that picture. Water ice is enormously valuable on a planetary surface because water is the feedstock for almost everything a settlement needs. Drinking water, obviously, but also oxygen via electrolysis and hydrogen for fuel cells and propellant. Polar ice at the Moon is a real, confirmed, accessible resource. The Moon also has helium-3 embedded in the regolith over billions of years of solar wind exposure. Helium-3 is interesting as a theoretical fusion fuel, though fusion power capable of using it remains in the future. So helium-3 is a potential long-term asset rather than an immediate practical resource. What the Moon doesn't have is an atmosphere. No nitrogen, no carbon dioxide, no buffer gas at all. If you want to breathe inside a lunar habitat, every molecule of that breathable air has to come from somewhere. From Earth, or extracted from the ice and regolith at significant energy cost. The Moon offers a water source but not an air source, and when you're thinking about long-term settlements, the continuous resupply of atmospheric gas is an enormous ongoing burden. The lunar resource picture, real water ice at the poles, helium-3 as a long-term wildcard, no atmosphere at all, dependent on Earth or ICU for everything that isn't water adjacent. Mars. This is where Mars actually gets some of its honest points, and it deserves them. Mars has water. Subsurface water ice has been confirmed at multiple locations, and the polar ice caps contain enormous quantities of frozen carbon dioxide and water ice mixed together. Mars also has water in the regolith in some regions. The water resource on Mars is real and substantial, not just trace amounts in permanently shadowed craters. Mars has a carbon dioxide atmosphere. Thin? Yes. Dangerously thin for pressure purposes, but chemically useful. Carbon dioxide is a feedstock, you can split it. On Perseverance, the MOXIE instrument, the Mars Oxygen In Situ Resource Utilization Experiment did exactly this. It produced oxygen from the Martian carbon dioxide atmosphere directly on the surface in 2021. This was a genuine milestone, not theoretical, not a laboratory demonstration in a vacuum chamber on Earth, an actual device on the actual Martian surface pulling carbon dioxide from the actual Martian atmosphere and producing actual oxygen from it. The quantities MOXIE produced were small. It was a technology demonstrator, not a production unit, but the chemistry worked exactly as expected in the real Martian environment. So Mars can, in principle, produce breathable oxygen from local resources. That's a real and important point for Mars's resource column. Mars also has regolith, loose surface material, that could be used for construction. Packing regolith into walls and berms and roof layers provides radiation shielding, structural mass, and thermal insulation all at once. The regolith is everywhere. You don't have to import it. You dig it up where you are. But the Mars regolith has a problem, and it's one that came to light from an unexpected direction. The Phoenix lander, which arrived on Mars in 2008, was looking for signs of habitability in the Martian soil. And what Phoenix found, in addition to what it was hoping for, was perchlorates. Perchlorate compounds, salts of chlorate ions, are present in the Martian soil at concentrations that are toxic to human physiology. Specifically, perchlorates interfere with the thyroid gland. The thyroid takes up iodine, and perchlorate competes with iodine at the thyroid's uptake mechanism, disrupting thyroid hormone production, which affects metabolism, development, and a range of physiological processes. On Earth, perchlorate contamination is an industrial pollution problem that water treatment systems manage carefully. On Mars, the perchlorates are not contamination. They are the soil. They are everywhere, distributed through the regolith, present in the dust that the Martian wind kicks up and deposits on every surface, including the surfaces of habitats, suits, and equipment that humans would bring inside. A Mars settlement doesn't encounter perchlorates once and solve the problem. It encounters them continuously as an ambient condition of the environment. This doesn't make Mars settlements impossible. There are remediation strategies: heating regolith to thermally decompose perchlorates, chemical treatment, filtration systems. But it means that the soil everyone was hoping to farm, the visions of Martian greenhouses and underground hydroponic gardens fed by local soil, those visions have a complication built into the ground itself. The soil is toxic. Every kilogram of Martian soil that enters a habitat carries a potential health hazard that requires careful management. The ground fights you. So Mars's resource picture confirmed water ice, a proven oxygen production pathway from the CO2 atmosphere through MOXIE, regolith for construction, but no nitrogen buffer gas and toxic perchlorates throughout the soil. Mixed, genuinely mixed, Venus cloud decks. The resource picture here is limited in a specific way that follows directly from the location. At 50 kilometers altitude, you are in an atmosphere of carbon dioxide mostly. The same carbon dioxide feedstock chemistry that MOXIE demonstrated on Mars applies here too. You could produce oxygen from the local atmosphere. Solar power at Venus is actually quite good, because Venus is closer to the Sun and receives considerably more solar energy per square meter than Mars does, even accounting for the cloud cover reflecting some of it. The HAVOC concept identified solar power as a viable energy source for cloud deck habitats. But the solid resources, the ones you'd need for building, for manufacturing, for long-term material independence, those require going down to the surface and coming back up. And the surface is 465 degrees Celsius under 92 bar of pressure, an environment that destroyed every probe we've ever sent there within 2 hours of landing. The Venera series of Soviet probes, the most successful surface missions to Venus, managed to operate on the surface for roughly 30 minutes to 2 hours before succumbing to the conditions. Mining the surface of Venus and transporting materials up 50 kilometers through concentrated sulfuric acid clouds is not a near-term realistic proposition. Venus offers breathable air temperature existence in a bubble with solar power and atmospheric chemistry, but without access to the solid material foundation that long-term settlements typically build on. You float. You are fed by what's around you in the gas. And for anything more substantial, you depend on what you brought. Titan. This is the one that changes the frame completely when you see the whole picture. Let's start with what's on the surface and in the sky. Titan's atmosphere is approximately 95% nitrogen. 95%. The atmosphere of Earth is approximately 78% nitrogen. The primary buffer gas in the air you're breathing right now, the gas that makes up the bulk of your atmospheric environment, the thing that keeps the oxygen from being too concentrated and combustible, nitrogen, is freely available on Titan in vast quantities, right there in the atmosphere. No extraction required. If you're building a habitat on Titan and you want to fill it with a breathable air mixture, oxygen and nitrogen in roughly the right proportions, the nitrogen half of that equation is, in effect, free. It's what you're already breathing on the surface through the atmospheric pressure system that's at 1.5 bar and already comfortable from a pressure standpoint. The Huygens probe's gas chromatograph mass spectrometer, the GCMS instrument, measured Titan's atmospheric composition during its descent through the atmosphere in January 2005, and the nitrogen dominance was one of the clearest signals in the data. 95% nitrogen, with methane as the second most significant component, and trace amounts of other hydrocarbons and nitrogen compounds. Which brings us to the second extraordinary feature of Titan's surface resource base: methane, ethane, liquid hydrocarbons. On Earth, hydrocarbons are buried under rock, and we drill for them, and they are the chemical foundation of the energy economy that built the modern world. On Titan, they are on the surface, liquid, in lakes and seas, right there. The Cassini radar mapping of Titan's surface, accumulated over years of flybys, revealed something that looked, at first, almost impossible. Large, smooth-edged features that the radar return indicated were liquid surfaces. Not solid. Not dry lake beds. Liquid. And the atmospheric and temperature conditions on Titan made the identity of those liquids clear. Methane and ethane, hydrocarbons that are gases on Earth but that exist in liquid form on Titan's cold surface, the way water exists as liquid on Earth's warmer surface. Kraken Mare, Ligeia Mare. These are the names given to two of Titan's large liquid hydrocarbon seas. Kraken Mare is estimated to be larger than the Caspian Sea on Earth, not a pond, not a lake in the modest sense, but a sea of liquid methane and ethane sitting on the surface of Titan in the polar region. Ligeia Mare, also near the North Pole, is smaller but still comparable to some of Earth's Great Lakes in scale. These are not metaphorical resources or theoretical deposits. They are mapped features on Titan's surface, observed by Cassini's instruments over years. What does liquid methane mean for a settlement? Methane is fuel. It is the simplest hydrocarbon, one carbon atom, 4 hydrogen atoms, and it burns cleanly, releasing energy. It is also a feedstock for chemistry, the starting material for a wide range of chemical synthesis pathways, the foundation of plastics and polymers and lubricants and countless other compounds. A settlement with access to essentially unlimited liquid methane has access to chemical energy and chemical manufacturing feedstock in a way that no other world in this comparison can match. Mars doesn't have surface hydrocarbons. The Moon doesn't have them. Venus has them locked in an atmosphere you can't land in. On Titan, you could theoretically drive a vehicle to the shore of Kraken Mare and pump fuel into it directly from the sea. But here's the thing about burning methane on Titan that requires careful thinking. Methane burns when combined with oxygen. Titan's atmosphere has no free oxygen. It's 95% nitrogen and then methane with no oxygen component. So the methane lying in lakes on Titan's surface is not spontaneously combustible. It is chemically stable in its environment because the oxidizer that would make it burn is absent. This is simultaneously a safety feature and a constraint. You can't just light a fire in Titan's open air, and habitats would need to produce or carry their own oxygen. If oxygen escapes from a habitat into the methane-rich air outside, you have the ingredients for combustion, which means the interface between a habitat's oxygen-containing interior and Titan's methane-containing exterior is a boundary that requires very careful management. No oxygen leaks outward, no methane leaks inward unless carefully controlled. But the methane isn't going to explode on its own out there on the plains. The surface is chemically stable, waiting. Beneath the surface, the picture gets more interesting still. Cassini's gravity measurements and radar observations built up a model of Titan's interior over the mission's lifetime. The evidence points to a subsurface ocean, liquid water, likely mixed with ammonia, beneath the icy outer shell of Titan's crust. Titan, in this model, is an ice-encased world with a liquid water layer somewhere below the surface, kept from freezing by radiogenic heat from Titan's rocky core. The water isn't accessible at the surface. You'd need to drill through ice to reach it, and the depth to the ocean is not known with precision. But the implication is that water is present in quantities somewhere below you. More immediately, the surface bedrock of Titan is water ice, not rock in the silicate sense, ice, which means that as an engineering and resource material, the ground itself is a water source. If you can melt it, you are literally standing on frozen water. If you need water, and a settlement always needs water, you melt the ground under your feet. So the Titan resource picture, fully assembled, a nitrogen atmosphere that provides your buffer gas freely, liquid hydrocarbon seas on the surface for fuel and chemical feedstock, a subsurface water ocean as a long-term water reservoir, and ice bedrock as an immediate water source that is everywhere. There is no world in this comparison with a resource profile even close to this. Mars has water and CO2 but no hydrocarbons and toxic soil. The Moon has water ice at the poles and essentially nothing else. Venus's cloud decks offer atmospheric chemistry but no solid resources and no surface access. Titan has more to offer a settlement, in pure resource terms, than any other world we've compared, and it offers those resources without the radiation problem, without the pressure suit requirement, without the toxic soil, without the acid clouds. The only thing it doesn't offer is warmth. And warmth, as we said, is the one problem humans have been solving since they discovered fire. Nuclear power in the form of RTG systems has already been tested, already worked, already operated in the outer solar system environment where Titan sits. Cassini's power came from RTGs. The waste heat from a nuclear power source on Titan's surface doesn't need to be radiated away. It's your heating system. The energy solution and the thermal solution are the same physical thing. Every watt of nuclear power you generate, you use. Nothing is wasted managing excess heat the way it would be closer to the sun. There is also, and this is one of those details that comes up only when you look carefully at the full Titan picture, the question of solar power, or rather, its near total absence. Titan receives roughly 1% of the sunlight that Earth receives. Saturn is nearly 10 times farther from the Sun than Earth is, and sunlight falls off with the square of distance, which puts Titan at about 1/100th of Earth's insolation. Solar panels, the technology that has powered so much of Earth's clean energy transition and so many spacecraft in the inner solar system, are essentially useless on Titan. The light levels are too low, which means, and here is where the constraint becomes a clarification rather than a problem, Titan forces you to nuclear power not as one option among several, but as the obvious, practical, only realistic energy base. And nuclear power produces heat, constant heat, day and night, through the 94 Kelvin surface temperature, through the 16-day Titan day-night cycle, through whatever weather Titan's methane cycle atmosphere produces. A nuclear-powered settlement on Titan is warm because its power source is warm. The settlement's heating system isn't an add-on, it is the settlement's power system. This is the unexpected connection that the temperature section was building toward, and now it's arrived. The thing that seems to make Titan hardest, the cold, is solved by the thing Titan makes necessary, nuclear power, which is also solved by the thing Titan makes plentiful, the waste heat from that nuclear power source. It is a closed loop of necessity and solution. Cold demands heat. Heat requires energy. Energy on Titan means nuclear. Nuclear produces waste heat. Waste heat is heat. Cold is solved. No other world in this comparison has this property. On Mars, a nuclear power source's waste heat would be a problem. You'd need to get rid of it, and the thin atmosphere makes radiative cooling the primary path, adding complexity. On the Moon, similarly, thermal management of a nuclear source is a design challenge, not a built-in solution. On Venus's cloud decks, you don't need the heat, so nuclear power would require active cooling, and the nearby solar resource is already more practical. Only on Titan does the energy solution and the thermal solution collapse into the same system. 2 metrics down, pressure and radiation, with Titan leading both. 1 metric, temperature, where Titan has the worst raw number but the most solvable engineering profile and a remarkable built-in solution through its own energy constraints. 1 metric, resources, where Titan has the richest and most diverse local resource base of any world we've compared. The pattern that started forming 2 metrics ago is now clearer, and we are not done. There are still the boundary conditions, gravity, transit time, the safety considerations that don't fit neatly into one column. And the final accounting, the verdict, But before we get there, stay for a moment with what the resources section has assembled, because it's worth seeing it whole in one place before we move on. A world with 1.5 bar surface pressure requiring no pressure suit. A world with the thickest natural radiation shield of any solid surface in the solar system. A world with a uniform, predictable, engineering manageable cold as its primary thermal challenge, addressed by the power system it requires anyway. A world whose atmosphere is 95% nitrogen, the buffer gas your lungs are already full of. A world with surface seas of liquid hydrocarbons larger than the Caspian Sea. A world with ice bedrock you can melt for water. A world with a subsurface liquid water ocean somewhere below. That is Titan right now, not after terraforming, not after a century of orbital mirror arrays and atmospheric seeding and planetary-scale engineering projects of the kind that live in science fiction. Right now, as it is today, as Cassini measured it, as Huygens descended through it in January 2005, as the data sitting in scientific archives describes it. The catch is the cold and the distance is next. So let us talk about distance and gravity and the boundary conditions that sit at the edges of our 4-metric scorecard and press on everything else. Because the scorecard so far has been almost unfair to Titan in how well it reads, and fairness demands that we look at the full picture. The cold is the obvious catch, and we've sat with it honestly. But there is another catch, quieter in the headlines, more decisive in practice, and it sits not on Titan's surface but between here and there in the empty dark of the outer solar system. The distance is not a minor inconvenience. It is the most daunting single fact about Titan as a destination. When the Cassini spacecraft left Earth in October 1997, it did not fly straight to Saturn. It couldn't. Not with the propellant loads we can reasonably carry. Instead, it looped around Venus twice, back past Earth once, out to Jupiter for a final gravity assist. A long, elegant, gravity-borrowing arc through the inner solar system before it finally arrived at Saturn in July 2004. 7 years, nearly 7 years of travel using the most efficient trajectory available with the technology of its era, aimed at a spacecraft that needed no food, no water, no breathable air, no gravity to keep its bones from thinning. A crewed mission to Titan with current propulsion would face something in that range. Roughly 7 years one way. That is not a journey, that is a life chapter. You would leave Earth a different person than you arrive. Children would grow. Parents would age. The world would shift in ways you couldn't follow, filtered through a signal that takes anywhere from roughly 40 minutes to over an hour to travel each way at the speed of light, depending on where Saturn sits in its orbit relative to Earth. You would be, in a very real sense, unreachable. Not delayed, unreachable. Compare that to Mars, which sits somewhere between 6 and 9 months away, depending on the orbital window. A long submarine deployment, a difficult winter at a polar research station, but a human-scale journey. People have done things harder than 6 months of confinement and come back changed, but intact. Compare it to Venus, whose cloud decks are 3 to 5 months distant, slightly closer than Mars on average. And compare it to the Moon, which sits just 3 days away, so close that the Apollo missions, some of the most complex engineering projects in history, managed round trips in under 2 weeks. The Moon is the only world where, if something went wrong, you could conceivably be home before the crisis became fatal. That contrast is not abstract. 3 days versus 7 years is not a difference of degree. It is a difference of kind. It changes the nature of the enterprise entirely. So when we rank Titan, and we will rank it, transit time is a genuine asterisk, a disqualifying one for near-future crewed missions, a solvable one perhaps for future propulsion technologies, advanced nuclear thermal drives, nuclear pulse systems, or propulsion concepts that currently exist on paper and in physics literature, but not in flight-ready hardware. The physics does not forbid a faster journey. Engineering has simply not caught up yet. But for the question as it stands today, with the rockets and the propulsion systems that currently exist or are credibly in development, 7 years one way is the decisive penalty Titan pays. It is not a small caveat, it is the largest single obstacle to treating Titan as a near-term target. And gravity. We should talk about gravity because it shapes everything from your daily life to your long-term health, and all 4 of our worlds sit somewhere interesting on that axis. Titan's surface gravity is 0.1 G, 14% of Earth's. You would weigh, if you weighed 70 kilograms on Earth, just under 10 kilograms on Titan. This sounds delightful until you remember that your skeleton and your muscles and your cardiovascular system spent hundreds of millions of years of evolutionary history calibrating themselves against a 1G world. Low gravity is not neutral. It causes bone loss, muscle atrophy, cardiovascular deconditioning. Fluid shifts toward the head that affect vision and intracranial pressure. We know this from astronauts on the International Space Station, where 6 months at 0 gravity requires months of rehabilitation on return to Earth. Long-term low gravity, not 0 but still low, is less well understood, but the concern is real and the research is sparse. We simply do not know with confidence what living at 0.14 G for years or decades does to a human body. It might be manageable with exercise regimes and medical monitoring. It might not. The Moon sits at 0.16 G, nearly the same as Titan, just slightly higher. The same concerns apply, same unknowns, same evolutionary mismatch. Mars offers 0.38 G. Better. Still not Earth normal and still insufficient in ways we cannot fully predict, but more than twice what Titan offers. There's a reasonable argument that Mars's gravity, while still low enough to worry about long-term, is within a range where the body might adapt reasonably well, particularly with rigorous physical countermeasures. We don't know this either, but the number is less alarming. And Venus's cloud decks sit at approximately 0.9 G, nearly Earth normal. The cloud habitat at 50 to 55 kilometers altitude exists in a gravitational field very close to what your body evolved in. Of our 4 worlds, Venus wins this category clearly and without competition. If your primary concern is what low gravity does to a human body over the decades, Venus is the only option that doesn't ask you to find out the hard way. So add gravity to the ledger. Venus scores well. Mars is imperfect but workable. Titan and the Moon trail on a metric whose long-term health implications we genuinely cannot fully predict. Now, there are safety considerations that don't fit cleanly into pressure or radiation or temperature, but that any honest accounting has to address. Because each of these worlds has a specific, non-obvious hazard profile that would shape daily life in a settlement, and leaving them out would be incomplete. On Titan, the hazard that keeps engineers thinking is the methane. Not because Titan is going to spontaneously combust, it won't. The surface has no free oxygen. There is nothing to sustain combustion without importing an oxidizer. The methane lakes sit there calmly, and the methane-nitrogen atmosphere moves in slow winds and periodic drizzle cycles that Cassini observed over years, and none of it burns because fire requires fuel and oxygen together, and Titan has the first, but not the second. But a habitat on Titan would need oxygen. Your lungs need it. Life support systems produce it. And oxygen is exactly what you do not want leaking into a methane-rich atmosphere. The engineering challenge is not that Titan might burn around you. It's that if you are careless with your oxygen systems, if a seal fails, if a tank ruptures and vents into the environment rather than back into the habitat, you could create locally flammable conditions near the habitat itself. The safety spine of a Titan settlement would be rigorous, obsessive containment of oxidizers, every seal checked, every system redundant, every oxygen handling protocol treated with the same seriousness a submarine treats its hull integrity. It is a solvable engineering problem. It is not a trivial one. On Venus, the hazard profile is different in character and strange in its details. Because the cloud decks of Venus, the seemingly mild zone at 50 to 55 kilometers, where temperature and pressure conspire into something almost pleasant, are made of concentrated sulfuric acid, the clouds themselves. The fog that surrounds a floating habitat is not water vapor. It is sulfuric acid droplets capable of dissolving many materials on contact, capable of causing severe chemical burns on skin and in lungs. The Venera probes, Soviet spacecraft that actually descended into Venus's atmosphere, gave us direct measurements of this. The chemistry is real and aggressive. So a habitat in Venus's cloud decks would need to be entirely acid-resistant on its exterior. Materials science would be a primary constraint. A hull breach in a Venus cloud habitat is not the same as a hull breach in a Mars habitat or on the Moon. On Mars, a breach is a pressure event. Air rushes out, you have minutes depending on the volume. On the Moon, same dynamic. On Venus's cloud decks, a breach is simultaneously a pressure event and a chemical exposure event. Sulfuric acid mist entering the habitat. That changes the response protocols and the material requirements in ways that add complexity the other worlds don't have. And Venus has another problem that the cloud deck optimism sometimes glosses over. There is no ground, there is no surface you can set down on. Below the cloud decks lies a world where the pressure climbs to 92 bar, equivalent to standing nearly 900 meters underwater on Earth, and the temperature exceeds 460 degrees Celsius. The Venera probes that managed to land on the surface survived for a few hours at most before the conditions destroyed them. So a cloud city on Venus is permanently, irreversibly airborne. You cannot touch down in an emergency. You cannot mine from the surface below. You float or you fall into conditions that are immediately and catastrophically fatal. The engineering must therefore account for a world in which there is no ground to return to, ever. That is a particular kind of cognitive and logistical pressure that is easy to underestimate. And on Mars, the world at the center of the popular imagination, the world whose settlement has been discussed in serious engineering papers and corporate roadmaps and congressional testimony for decades, the hidden hazard is in the dirt. The Phoenix lander, NASA's mission that touched down on Mars's northern plains in 2008, confirmed the presence of perchlorates in the Martian regolith. Perchlorates are chlorine-containing compounds, and they are toxic to humans, specifically to the thyroid gland. They interfere with iodine uptake, which disrupts thyroid hormone production, which affects metabolism and development, and a cascade of other physiological systems. The concentration Phoenix found was roughly 6% by weight, not an immense amount, but enough to be a serious concern in a settlement context, because on Mars the dust is everywhere. Martian dust storms are real and documented and sometimes global. The dust is fine enough to penetrate most ordinary seals. A habitat on Mars would need to manage dust ingress constantly, not as a theoretical concern, but as a daily operational reality. And if that dust carries perchlorates, and it does, then contamination of food-growing systems, of air supplies, of skin and clothing becomes a genuine health management problem over the long term. There are remediation techniques, washing, chemical treatment, bacterial processes that some research suggests could break down perchlorates, but none of them are trivial, and all of them represent a sustained burden that a settlement must maintain indefinitely. The soil of Mars is not neutral. It is actively trying, in its quiet chemical way, to harm the people who try to build a life on it. So now we have the full picture. All four worlds, all the metrics, all the catches. Let's put it together. Let's actually score it. Pressure. Titan wins cleanly, completely, without serious contest. 1.5 bar. No pressure suit required outdoors, just warmth and oxygen. Mars sits below the Armstrong limit, requiring a full pressure suit at all times outdoors, with the added knowledge that suit failure is immediately and violently fatal within seconds. The Moon requires the same. Venus's cloud decks offer approximately 1 bar at altitude. Earth-like, competitive with Titan, but floating above an uninhabitable surface. On pressure, Titan and Venus's cloud decks are the winners. Mars and the Moon are losers on the hardest-to-solve metric, the one where failure means instant death. Radiation shielding. Titan wins again, 10 times more atmospheric mass per unit area than Earth. The thickest natural radiation shield of any solid surface in the solar system, enhanced by Saturn's magnetosphere when Titan passes through it. Surface radiation is extremely low, lower than on Earth's surface in some estimates. Mars, with no global magnetic field and a 6 millibar atmosphere that provides almost no shielding, accumulates roughly 7 millisieverts per day as measured by Curiosity's RAD instrument. Around 500 days on the Martian surface approaches a career radiation limit, meaning that a long-term settler on Mars is absorbing radiation at a rate that meaningfully raises cancer risk over years of exposure. The Moon is worse still. No atmosphere, no magnetosphere, full exposure to galactic cosmic rays and unshielded solar particle events, measured by Chang'e-4's LND instrument as roughly 1.3 times the equivalent dose rate of the International Space Station and far higher during major solar storms. Venus's cloud decks offer decent shielding from the atmospheric column above 50 kilometers, though without a magnetosphere, and with the relevant measurements less thoroughly studied than Titan's. On radiation, Titan wins clearly. Mars and the Moon carry genuine long-term health costs that their atmospheres and magnetic environments cannot mitigate. Venus's cloud decks are middle ground. Temperature. Here, Titan loses. 94 Kelvin, minus 179 degrees Celsius, minus 290 degrees Fahrenheit. This is the coldest surface of our 4 candidates and the most challenging thermal engineering problem. Mars, ranging from about +20 at equatorial noon down to below minus 125 at the poles, with an average around minus 63 Celsius, is cold but manageable by the standards of hardware we already deploy. Mars rovers operate in those temperatures. The Moon swings more violently, plus 120 Celsius in direct sunlight, minus 170 in the lunar night, and down toward minus 240 in permanently shadowed polar craters. That thermal cycling stresses materials and requires substantial engineering attention. Venus wins on temperature. The cloud decks at 50 to 55 kilometers sit at roughly 0 to 50 degrees Celsius, the most Earth-like temperature of any location in the solar system outside Earth itself. A shirt-sleeve environment in terms of thermal comfort, which is remarkable and a little disorienting when you remember what lies 60 kilometers below. Resources. Titan wins with breadth that no other candidate approaches. The nitrogen atmosphere. 95% nitrogen, the same buffer gas filling your lungs right now, available freely and abundantly, the feedstock for breathable air, mixtures without any chemical separation work of consequence. The liquid hydrocarbon seas, Kraken Mare and Ligeia Mare, methane and ethane sitting in open bodies larger than any lake on Earth, chemical energy and feedstock lying on the surface, accessible without drilling or excavation. The water ice bedrock, meltable for water without the deep polar mining operations the Moon requires. The subsurface liquid water ocean, still poorly characterized but real, confirmed by Cassini's gravity measurements. Mars offers confirmed subsurface and polar water ice, the demonstrated ability to produce oxygen from carbon dioxide via MOXIE on Perseverance in 2021, and regolith for construction. A genuine and useful resource base, but one complicated by toxic perchlorates in that same regolith. The Moon offers polar water ice and helium-3 in the regolith, but no atmosphere at all. No buffer gas, nothing free. Every resource requiring active extraction. Venus's cloud decks offer carbon dioxide and sulfuric acid, but no solid surface to mine and very limited accessible material resources. On resources, Titan leads. Gravity. Venus's cloud decks win at approximately 0.9 g, nearly Earth normal. Mars offers 0.38 g, imperfect, but the best of the solid surface candidates. Titan and the Moon both sit around 0.14 to 0.16 g, the most challenging for long-term human health with the most uncertain consequences. Transit. The Moon wins absolutely. 3 days. A human-scale journey, the only world close enough to imagine genuine resupply and emergency return. Mars is 6 to 9 months, difficult but achievable and already within the planning horizon of existing space programs. Venus is 3 to 5 months, slightly shorter on average than Mars and not dramatically different. Titan is roughly 7 years with current propulsion, the same trajectory that carried Cassini through its planetary pinball tour of the inner solar system. 7 years is not a trip, it is a deployment, an era, and it is Titan's decisive penalty. Now, the verdict. If you ask the question the way it is usually asked, which world should we go to next in the near term, with the technology we have or credibly expect to have in the next few decades, the answer is not Titan. The transit penalty is disqualifying for near-term crewed missions. 7 years is too long, the radiation exposure during transit is its own problem, the supply chain is impossible to maintain, and the communication delay makes real-time support from Earth a fiction. Mars and the Moon are the practical near-term candidates, and between them, the Moon's proximity makes it the more rational stepping stone for developing the techniques and technologies that every other destination requires. But if you ask the question the way this video has been asking it, which world offers the most naturally supportive environment for human long-term settlement, scored on the physics of keeping a body alive, the answer is genuinely surprising. And it is worth sitting with how surprising it is, even if you've been listening for the past hour and have watched the scorecard assemble piece by piece. Mars, the world at the center of the popular imagination, the world whose settlement has been discussed in congressional hearings and corporate roadmaps and serious academic papers for the better part of 50 years, the world whose ruddy face has been painted on the walls of children's bedrooms and stamped onto mission patches and invoked in presidential speeches about humanity's destiny. Mars loses on 2 of the 4 metrics that most directly determine whether a human body survives and stays healthy over the long term. It loses on pressure, 6 millibars below the Armstrong limit, every outdoor moment, a suit failure away from ebullism, from the water in your own tissues boiling at body temperature. That is not a manageable engineering challenge in the way that cold is manageable. A suit failure on Mars kills in minutes. There is no gradual onset, no warning window, no way to retreat to safety and recover. The physics is absolute. It loses on radiation, no magnetosphere, inadequate atmosphere, 0.7 millisieverts per day, accumulating in the body with no prospect of mitigation short of living underground permanently or behind thick shielding that must itself be manufactured and transported or constructed from that perchlorate-laced regolith. A long-term Mars settler is aging their radiation lifetime faster than they would on Earth, faster than they would on Titan, far faster than they would in Venus's cloud decks. Cancer risk, cognitive risk, the long, slow accumulation of damage that the thin air cannot stop. Titan, by contrast, loses on one of the four metrics. Temperature. 94 Kelvin. The cold. And here is the thing about the cold, that this whole comparison has been quietly assembling since we first mentioned nuclear power. Titan gets roughly 1% of Earth's sunlight. At Saturn's distance, the Sun is a bright star in a dark sky, insufficient for solar panels, irrelevant as a power source for anything requiring serious energy output. So a Titan settlement needs nuclear power. There is no practical alternative. Radioisotope thermoelectric generators of the kind that powered Cassini itself, or small fission reactors of the kind that current space agencies are actively developing for lunar and Martian surface power, or some combination. Nuclear power on Titan is not a speculative addition. It is the obvious, necessary, physics-determined first choice. Nuclear power produces heat as a byproduct, always. Every nuclear system, from an RTG to a fission reactor, generates thermal energy as part of its operation. On Earth and on the Moon and on Mars, where thermal management often means getting rid of excess heat, this byproduct is a problem to manage. Radiators, heat exchangers, cooling systems, engineering infrastructure devoted to removing the heat the power system produces. On Titan, the heat you need to stay alive is exactly the heat the power system produces. The nuclear reactor that keeps your habitat powered also keeps it warm. The waste heat that every other environment treats as a liability is, on Titan, the solution to your primary survival challenge. You are not running two separate systems, a power system and a heating system. You are running one system that does both. The reactor that produces your electricity produces your warmth as a side effect. Cold is the one problem humans have been solving since they understood fire, the one challenge where every possible tool in the engineering toolkit already exists: insulation, heating elements, thermal mass, waste, heat recovery. The accumulated centuries of cold climate engineering that anyone who has designed a building in Siberia or a pipeline in northern Alaska has contributed to. And on Titan, you get all of that from the same box that keeps your lights on. This is the unexpected connection that the scorecard alone cannot capture. The one thing Titan lacks, sunlight, creates the power strategy, nuclear, that addresses the one problem Titan has: cold. Titan's greatest weakness and Titan's primary survival challenge are connected by a single engineering solution that already exists and is already being developed for space use. Mars's problems are not like that. The radiation has no byproduct solution. There is no engineering system you can bring to Mars whose waste product is a magnetic field. The pressure has no equivalent reframe. You cannot bring something to Mars whose byproduct is atmospheric thickness. The problems Mars has are problems you bring countermeasures to. On Titan, the problem and the solution arrive in the same package. So what is the honest verdict? The Moon is the right first step, not because it is the most hospitable. It is not. It scores poorly on pressure, radiation, temperature, and gravity, but because it is close enough to allow the iterative, failure-tolerant engineering development that every more ambitious destination demands. 3-day transit, emergency return, real-time communication with Earth. The Moon is the testbed, the proving ground, the place where humans learn to keep themselves alive away from Earth before the distances become incompatible with error. Venus's cloud decks are a genuinely underappreciated candidate. Earth-like temperature, Earth-like pressure, near-Earth gravity, decent radiation shielding, a location in the inner solar system reachable in 3 to 5 months. The sulfuric acid clouds are a genuine engineering constraint, and the absence of any solid surface is a genuine operational constraint. But in terms of human comfort and physiological compatibility, the cloud decks at 50 kilometers altitude are surprisingly compelling. The HAVOC concept from NASA Langley is not science fiction. It is a serious engineering study of a real possibility. Venus deserves more of the popular imagination than it currently gets. Mars is the most credible near to mid-term destination for a surface settlement, and nothing in this scorecard changes that practical reality. The propulsion and life support technology being developed for Mars is real, advancing, and on a timeline that connects to the current generation of engineers and mission planners. The 6 to 9 month transit is hard but human scale. MOXIE demonstrated oxygen production on the surface in 2021. Subsurface ice is confirmed. Regolith is available for construction even if its perchlorates require remediation. Mars is a very hard place to live, harder than the promotional materials suggest, with radiation and pressure problems that its thin air cannot solve, but it is reachable. And Titan. Titan is the most hospitable solid surface in the solar system for a human body, measured on the metrics that actually determine survival. It is not even particularly close on pressure and radiation. The 1.5 bar surface is survivable in thermal protection and an oxygen mask. The thick, nitrogen-heavy atmosphere blocks radiation that would accumulate fatally on Mars in under 2 years. The hydrocarbon seas and ice bedrock and nitrogen air provide a resource base of extraordinary richness. The same nuclear power that is the only rational energy choice is also the heating solution for the only metric Titan loses. The honest summary is this: if you could transport a settlement to Titan instantly, or nearly so, Titan would likely be the best home for long-term human life of any world we've discussed. The environment is more naturally compatible with human biology on more axes than any other candidate, but you cannot transport a settlement instantly. 7 years of transit with current propulsion is a genuine, possibly temporary, but currently decisive disqualifier for crewed missions. It depends on what you are optimizing for. Near term, near future with current technology. Moon for development, Mars for the first off-Earth settlement. Longer term, with propulsion advances and the willingness to spend that transit time. Titan's scorecard says something the popular imagination has not caught up with yet. The counterintuitive result is real. The contrarian case holds up under the physics. Mars first makes sense as a pragmatic answer to a question about what is reachable, but Mars first as a statement about what is best, about which world has the most to offer a human body trying to survive for decades away from Earth, does not survive contact with the data. The data points, quietly, and with the kind of certainty that mission instruments and planetary science have accumulated over decades of close observation, at a cold moon orbiting a ringed planet in the outer solar system that almost nobody puts on the poster. And somehow that seems right for a sleep video. The universe's best-kept secrets are the ones that require patience to reach. The ones that don't announce themselves, the ones that sit quietly at Saturn's distance, wreathed in orange haze, waiting for the measurements to accumulate and the scorecard to fill in, and the counterintuitive answer to become unavoidable. Titan has been waiting a long time. It has a patience that cold places tend to have. So, we've come a long way tonight. All the way to Saturn's largest moon and back, stopping at Mars and the Moon, and the unlikely paradise floating in Venus's acid clouds along the way. We've scored 4 worlds on 4 metrics. We've watched the popular answer, Mars, obviously Mars, hold up on some axes and falter on others. We've watched the surprising answer, Titan, improbably, counterintuitively, the wrong answer until it becomes the right one, assemble itself fact by fact until the scorecard is hard to argue with. Pressure, radiation, temperature, resources, gravity, transit. Each world has its column and the numbers fill it honestly, without favoritism for the world the movies picked, or the promoters chose, or the distance made familiar. And somewhere in all of that arithmetic, something that is not quite arithmetic happens. The kind of thing that tends to happen when you follow a question honestly to wherever it leads. You realize that the solar system is not arranged according to our preferences. It did not put the best candidate closest to us. It did not put the most hospitable surface at the most convenient distance. It placed extraordinary richness at Saturn's distance, under an orange sky beside liquid methane seas, in a cold so deep and so clean and so absolute that it has the quality of something permanent. And it placed the Mars we've been dreaming about at the edge of survivability, on half the metrics that matter, close enough to reach but no more naturally hospitable than a place that requires us to solve its problems rather than inherit its gifts. The universe is not cruel, it is just not organized around human convenience. And there is something quietly wonderful about that, something that makes the enterprise of going out there, of looking seriously at the numbers and following them wherever they point, feel necessary in a way that comfort and proximity never quite capture. Wherever you are right now, whatever corner of this small, warm, 1G, 1 bar, liquid water on the surface world you've settled into tonight, you are on the most extraordinary planet we know of. Not because science says so in a consolation prize way, but because the comparison genuinely makes it so. The Earth has the pressure and the temperature and the radiation shielding and the gravity and the liquid water and the nitrogen air and the magnetosphere and the proximity to a star that provides free energy in enormous abundance. Earth wins every category. Earth is the scorecard champion by an enormous margin, and yet there are other worlds, harder ones, stranger ones, ones that require ingenuity and stubbornness and the kind of engineering patience that the people who built the Cassini spacecraft, that remarkable machine that looped around Venus twice and swung past Earth and borrowed Jupiter's gravity, and finally arrived at Saturn 7 years after launch to spend 13 years sending back pictures and measurements and the data from which this entire conversation was built. That kind of patience. The universe rewards it. Back at the beginning of tonight, wherever that was for you, we opened a question. Not just which world wins the scorecard, you know that now, but something underneath it. The question of what it means to take seriously the idea of living somewhere other than here. Not as a fantasy or a promotional campaign, but as a physics problem, a life support problem, a genuine reckoning with the 4 things that most directly determine whether a human body survives: pressure, radiation, temperature, resources. The answer was not the one the headlines suggest. And that seems like the right kind of thing to carry into sleep. Not a settled answer, a better question, the kind that comes from following the data honestly and finding that the universe had a different opinion than the poster on the wall. If this slow journey through the solar system helped you drift, or helped you think, or simply kept you company in whatever quiet hour this is for you, a like and a subscribe to Orbit Observer really does help. Small creators like this one rely on your support to keep the lights on and the narration going. And if you're still here, still listening, still somewhere between waking and whatever Titan dream might be forming in the back of your mind, leave a comment. Tell me where you are tonight and what time it is in your corner of the world. I read them. I appreciate every single one. Until next time, there's always another world to visit, another metric to score, another counterintuitive answer waiting at the end of an honest question. Good night from up here in orbit. I'll keep watch while you drift.